Hello, everybody, and welcome to another great day of chemistry. So last time we looked at the changes in internal energy of a system and how we can describe them in terms of work and heat. Today, we're going to really kind of break these down by looking at these changes in energy for a good model system, and that's just going to be the various types of compression or expansion of an ideal gas. And specifically, we're going to be looking a lot at work today. So let's get to it. So one of the best ways to try and analyze how energy moves in and out of a system is going to be to make use of a simple model. That means we're specifically going to be looking at an ideal gas. And then one of the best versions of this is going to be our piston, which I brought up several times, which again is just going to be a cylinder where I can expand or compress the volume of gas inside. Now, one of the best forms of pistons is where I'm going to be applying a pressure to the top of the container, which under large pressure should compress the system, and under low pressures, that gas should push back and the system should expand. But again, if I know what that force is, I can go ahead and model what happens. And then we can look at the changes in internal energy. So the internal energy can change based on heat and work. We're going to look at heat a little bit more next time. So let's go ahead and really focus in on this work term today. So we can look at this both in terms of the discrete variable, but also the infinitesimal. We're looking at infinitesimal changes or very small changes in the internal energy, the heat, and the work. So one of our simplest versions of this piston is going to be applying a constant force to the top of the piston. Easiest way to do this is literally to throw a weight on it. So you can imagine I have a nice piston that's at rest. I go ahead, put a weight on it, that's going to go ahead and compress. This is the same thing generally as putting a weight on a balloon. You can squeeze the balloon down. Now, when doing this, we're going to want to try and determine the work of the system. And as we stated previously, we can define the work based on the change in potential energy, as the potential energy is going to be the maximum amount of work I can apply out of the system. Now, because we're looking at the work the system does, this is going to be essentially the negative of the change of potential energy, or give me more or less negative F dx, where x is just going to be the height of the container, and F is going to be the force applied by the weight. Now, there's a couple of ways I can look at the force that a weight applies. So one of the classic descriptions from general physics is just going to be force equals mass times acceleration, where m is going to be the mass of the weight, and acceleration is just going to be due to gravity pulling that weight down. But there's also a much more useful term we can use here, which is force is also equal to the pressure being applied by that mass and the area it's being applied over, which is just going to be the cross-sectional area of this piston. You may be more familiar with this with the idea of pressure equals force divided by area, but in this case, we're trying to determine the force. This is also a natural equation for us to use because we already have several ways to look at the pressure of the system. So we'll often use pressure over force in many cases. So we can then go ahead and take this description of force, insert it into our work equation. And when we do, we find that the change in work is going to be equal to negative the pressure times the area times that change in height. Well, wait a minute. Area times the change in height, that's just going to be the change in volume. Because as this piston goes ahead and compresses, this piston will become smaller based on the height in which it fell and the area, cross-sectional area of the top of the piston. So this gets us into a much more pretty equation, because the change in work can be related as negative pressure times change in volume. So this is most commonly known as PV work. This is going to be our classic way of describing work that comes with the expansion or compression of a system, with changes in size. And a lot of chemical systems do have some degree of changes in size, so this will be our go-to description of work. It is worth noting there are several other kinds of work, like electrical work or a magnetic work, but they're much more nuanced. So we're going to be focusing on this PV work as our dominant feature for now. Now, big thing to note here is that first, this is infinitesimal changes. So in order to get the actual work, we're going to have to integrate the system over the change in volume. So again, it's from our starting volume to our ending volume. If we have a compression, the ending volume should be smaller than our starting, so we should have a negative delta V. The other very important thing to make note of is the pressure we're looking at here is known as the external pressure. It's the pressure that the mass applies. This is not going to be the pressure of the gas or the system. I'm going to differentiate the idea of the pressure of the system, which will often come with no subscripts, from the external pressure, which I'm going to always try and denote as pressure external. Do note that some resources will drop this subscript, so you have to be very careful when using a lot of these equations. So do be cautious when you're using other resources. Now, the nice part is that this external pressure will not change with volume because the amount of force being applied by weight is non-changing, which means that we can pull it out of our integral, which just gets us negative P times the integral of dV, which is just delta V. And the really beautiful thing is at this point, when coming up with this description, we are not paying any attention to whether the system is being compressed or if it's expanding. In a compression, this change in volume should be negative. The volume is decreasing, which would give me a positive work because I'm putting energy into the system. Under expansion, we would go ahead and expect this change in volume to be positive. It's increasing in volume, which will give me a negative work. Energy is leaving the system. But either way, we can go ahead and use this term either way. And as long as that pressure is constant, we can use the simplified P delta V version. So this will work for any case where we have a constant external pressure. However, what would happen if I go ahead, put the weight on there, compress the system, and then I took the weight off? Under this case, the system would go ahead and expand because I no longer have that force keeping the system contained. But as I said, we can still use our same equation. We can still do the integral of P dV. Now, in this case, we also get lucky because the pressure is still going to be constant. It turns out that the constant pressure being applied is 0. So this point, we've got no force resisting this expansion. And since that pressure is 0, that means the integral of P dV will also be 0. So a very important point is anytime we're doing a expansion under no resistance, or really any kind of movement under no resistance, the work of the system will always be 0. As a result, this is called a free expansion because nothing is resisting this change. And any free expansion requires no work. This will happen very naturally and typically happens very quickly. So and it is worth noting, almost all systems in practice have some kind of resistance. But sometimes this resistance is so low that free expansion becomes a very good model. So you can imagine if I have a nice balloon, I go ahead and I poke a pin in it, all that gas inside the balloon is going to quickly expand into the environment. So this will give me a free expansion. In practice, the air in the atmosphere will resist that change, but the amount of pressure it exerts on the balloon is usually so low we get to ignore it. So again, this is a bit of an extreme case, but a good model for a lot of real systems. Now, we have to worry about another pesky issue, because notice, in both of these cases, we treated that external pressure as constant. But what happens if that external pressure is going to change during the reaction? Now we've got a slight problem here. Because notice we have to take the integral of P dV. Well, if that pressure is changing, it probably has a volume dependency, meaning I can't pull that pressure out of the equation, which means I need to integrate it, which turns out we can't actually do unless we know the volume dependency of the external pressure, which means we need an equation to describe how that pressure changes with volume. Now, the easiest way to do this is to assume, hey, what if pretty much throughout this whole change, the external pressure and the system pressure were the same? So the pressure being put on the system and the pressure the gas in the piston has resisting that change, if they're identical, now I've got an equation. So in these cases, this is called reversible because what happens is if the pressure of the surroundings and the system are equal amount, that means I don't have a amount of pressure either causing the system to expand or to compress. And it can go either way. And so at this point, the system is called reversible because it could expand or compress. But either way, any change that would occur is going to occur very slowly. Because if you have two equal and opposite forces, they cancel each other out and nothing really happens. So that means that if the system does expand, it's going to happen because these are almost the same, just very slightly off. The closer they are, the more truly reversible a system is. In practice, no system is truly reversible, but like expansion, like free expansion, some get very, very close. Now, if I have a reversible system, that means I get to replace the external pressure with the pressure of the gas. So at this point, I'm going to go ahead and drop the subscript on the pressure to indicate we're now looking at the pressure of the systems, not the external pressure. Now, one of the problems that we still have is that with this reversible expansion, we still have this changing pressure. And so that can be very hard to predict. So we're going to need an equation to describe the pressure of the system. Well, hey, we spent chapter 1 developing some pretty good equations for the pressure of the system. So at this point, we can go ahead and pick our favorite equation of state to describe the gas inside the piston. Our go-to favorite is usually going to be the ideal gas. So now we know that the ideal gas is going to be related to the moles, the temperature, and the volume. And congratulations here. Now we have a volume dependency of the pressure. We know exactly how this pressure changes with volume. As the volume decreases, the pressure is going to increase. And there we go. So now we can insert our ideal gas equation or any equation of state that you wish into our work equation. Now, when we do this, we have kind of this fun term of nRT over V. But notice this is just with respect to changing V. So we can generally assume a closed system, at which point n is constant, we can pull it out. R is a constant, so we can also pull that out in front of the integral. Temperature, now here's the big approximation. We're going to assume the temperature doesn't change. So this is considered an isothermal system. So notice from here on out, all of the steps will assume the system is under constant temperature. It won't quite work for non-isothermal cases. But if we assume constant temperature, then we're left with an integral of dV over V. Oh no, it's been a while since Calc 2. So if we go ahead and review our integrals, we'll find that the integral of dV over V is just going to be the change in natural log of V. So this is going to be the natural log final minus the natural log initial, or V2, natural log V2 minus V1. We can then use our log laws to show that that's the same as the natural log of V2 over V1. So, congratulations. We now know how to describe the isothermal reversible expansion of an ideal gas. So notice we have a lot of caveats to derive this equation. It is also worth noting, though, because we're assuming the system is reversible, it should occur exactly the same for expansion or compression. So as a result, this same exact equation will also hold for the isothermal reversible compression of a gas. So now we've derived several examples of how we can look at the work for the expansion or compression of a system. So let's go ahead specifically look at this expansion idea. So if I have my piston, I want to figure out exactly how much work I can get out of the system as expanding, because this is exactly, as I said, how we can do things like drive a steam engine or a cannonball or a piston. So in this case, the most amount of work we can accomplish is letting this expansion occur reversibly, because at this point, as the gas is expanding, that pressure is slowly decreasing, and we're going to slowly push less weight as I go. So as a result, we can get the maximum amount of work out of the system. But notice, because of these reversible conditions, this also means that this will be the slowest way to do work because we're trying to make sure we get every single joule and push the most amount of weight at every step. And again, by looking at the integral of this PDV, we'll notice that this is going to be the largest area under the curve. Now, this is also the hardest and slowest to do. In practice, one of the easiest options is instead if we're uh, pushing a constant force. So let's say I again have a compressed gas, put a weight on top of it, and then just let the gas expand. It will expand very quickly at the beginning and then slowly till it comes to equilibrium. So again, the gas will stop expanding when the external pressure and the system pressure are equal. Notice this will occur much more quickly, but we're doing a lot less work. Under the far extreme, we could also just not let any force resist the expansion, at which point that piston will immediately pop all the way up to as far as it can, but we got no work out of the system, so it wasn't doing anything for us. So again, this is kind of that tricky bit. Now, it is worth noting, in practice, we're often going to be looking at a system that doesn't fall under one of these three extreme cases. In this case, we're looking at an irreversible work without a good equation for the external pressure. So we don't have a good way to describe the amount of work done by the system. So instead, we'll often use it to describe one of these three approximate cases to describe the system. Either we'll go ahead and set an external pressure that was fairly constant over the whole time, or take an average external pressure. Or we go ahead and focus on what's the maximum amount of work that we can do on the system, then measure the amount of work done and figure out a percentage effectiveness. But again, we're often going to approximate anything we do with one of these three extreme cases. Isobaric or constant pressure, free expansion, or isothermal reversible. So next time we're going to go ahead, take a little bit of a change of pace and look at a constant volume system so we can examine heat a little more closely. Till then, take care.